Now we will continue with our first talk by Vincent van Wingerden from Classiq. Before Classiq, Vincent worked as a technical architect at Microsoft, where he worked on various quantum computing projects. During this talk, he will discuss how companies can leverage quantum computing using the Classiq platform. Please welcome to the stage Vincent.
Yes, so thank you everybody for being here. As said, I'm Vincent, and today I will be talking about our Classiq platform. So, very quickly, who are we? Yeah? This is the green one?
The big green one.
Sorry. Okay, so who are we? We see ourselves as one of the leaders in the quantum software space. We are very heavily funded via VCs. We are based in, are headquartered in Tel Aviv. We have offices in Europe as well as in Asia. And we are already being heavily used in both the enterprise market, so the commercial space, as well as the educational market, which both I will touch on today. So let's have a look at what we do. But first, let's check what is the challenge that we would like to tackle. Maybe some people were already in this talk of Berlin Ingelheim a couple minutes ago. And he ended, I think, with the biggest challenge of all. If there is a quantum computer today with a very big size, who can actually program it? And I think with the current tools, the answer to that actually is no one. How we program today at this very low level is doable because the quantum computers themselves are also very small. So we still have the knowledge, we have the expertise to program these small computers. But what would happen if we would take a huge device with millions of qubits and 10,000s of physical qubits, who would be able to actually create an efficient quantum circuit for such a device? I think at the moment, with the current toolbox that we have, looking at the tools from various vendors, that it will be extremely hard to do so. And that is a challenge that we would like to tackle using Classiq. So how do we do this? So our approach is actually to create a layer of abstraction to the programming of quantum computers. So instead of programming at a gate level or at a very fixed block level, the idea of the Classiq platform is that we program a model. And the model is the functional description of your quantum program. So a lot of different programs have a lot of different algorithms have different steps in their algorithm. So for example, you would start with some state preparation, and maybe you have a step about QPE and all these type of things. And that is what you describe in a model at Classiq. So you, at a very high level, describe the functionality that you want to achieve. And what makes this so interesting is if you describe it at a high level, then a computer can take that high level input, and we call that computer our synthesis engine, and actually go from that high-level input and synthesize a block-based algorithm. So we can create a logical circuit. And what makes it so interesting is that because of that, we are very flexible in how we implement each functional block. So we don't need a fixed implementation every single time. Every time we target a new computer, we can change how we implement a functional block. And that makes it very interesting. And actually, the interesting thing here is we know we can scale. The technology that we are using is the same technology or very similar technology that's being used today when we design large CPUs and large GPUs, which have billions and billions of gates or transistors. So we go from our high-level model, or the description of our algorithm, we put it into our synthesis engine, and then we will actually get a visualization on how does that circuit look from a high level. And then you can also, if you want, if you're an expert, you can drill down deeper and deeper in how specific functionality has been implemented. And if you will try this platform, you will see that if you target different hardware, every time different parts of the algorithm are implemented differently. And that's the beauty of quantum computers. There's a lot of different ways how you can implement functionality. But that also makes programming very hard. And that is what we do for you. You never have to make that decision yourself. And once you analyze it, you can execute it anywhere you like. Our output can be CASM, Circ, Q#, whatever your preference is, and we can execute directly on the cloud as well. So how do you create that model? How do you create it? So firstly, we have two interfaces. We have a Python SDK, which anybody can use, and we have an online IDE, which is a very low-code environment, so you don't need to be a programmer to use this. So the tools that we make available are built-in algorithms, so completely pre-made blocks. So, for example, if you want to do Grover or anything like that, you don't have to do anything yourself. We provide pre-built building blocks, so with those blocks you can make one big algorithm, and we can have our completely you can build algorithms completely from scratch. When we can synthesize for any public quantum computer. So you can say, well, I want to target an IonQ device or Rigetti device or Quantinium or whatever you want, or maybe an IBM device. But the interesting thing is there are also researchers who haven't published their devices yet. So you as an end user can also say, well, I want this algorithm, and I'm thinking about creating a quantum computer, and I have this topology in mind, and these native gates. What would the logical circuit be? And so you have all the flexibility to change the hardware requirements, and our synthesis engine will create a logical circuit which fits that specific hardware as good as possible. And this makes it very future-proof. So you design your model once, and regardless whether new quantum computers will pop up, the only thing you need to do is set the new target, and we will generate a new logical circuit for that. And that makes it extremely future-proof, because regardless on the amount of qubits that there will be, we can actually generate that circuit. And as I said, we can execute it anywhere we like. So let's have a quick look at how it works. Unfortunately, I don't have a interactive demo with me, but I have some nice slides. So what you see here is actually a view of our IDE. And the first thing you see, what we're going to solve in this specific case, is we're going to use Grover to solve an arithmetic expression. So here on the right, you see an arithmetic expression, and I'm not sure if everybody at the back will see it, but it's an arithmetic expression which has three variables, A, B, and C. And the goal with this Grover algorithm is to find values for A, B, and C that satisfy this part of the equation to 4. So what do you need to do to generate a logical circuit that satisfies this? The only thing you need to do is write your expression. You need to give some definition on your variables, like do you want to have those variables be integers, or should they have floating points, or do they have signs, so can they be both positive as well as negative, some of those properties. And lastly, you can give a specification on your hardware. And that is what I said already. That gives our synthesis engine input on the connectivity between the qubits, on the native gates that that device has. And with that information, we can make the most ideal logical circuit. So this is the output. A complete oracle. You can see all the parts of the Grover oracle, Grover algorithm. We start in equal superposition. We have this automated generated oracle, and then we have our diffuser. This took a few seconds. You can do this without having any quantum experience. And we don't just have this for Grover, we have this as well as for financial functions, for chemistry, all these type of things. What we are trying to do is democratize quantum computing. So we want to make sure that not only if you have a PhD in quantum information systems, that you are able to use quantum computers, but also the programmer who is, or a financial analyst who wants to get an optimal strike price for his option, for example, can use this tool without needing to program, without needing to understand what is an Hadamard gate, what does my specific quantum computer do, and having to make decisions at a very low level. So that is what we're trying to do. This can be directly, so if we go back, we have a very big execute button, and the moment that button is pressed, you can check wherever you want to execute it. Whether it is any of the cloud providers where we are directly integrated with, or we can, maybe you have access to a local quantum computer, so there are some quantum computers scattered over Germany, or maybe you are working on one, you can execute the circuit that we just created in QASM and execute it there as well directly. So this is our promise. You create a model, and that lasts forever, instead of creating a circuit which you have to rewrite every single time that you want to target a new quantum computer. So let's, for the last few minutes that we have, I'll keep some time for questions. Let's look at some of the use cases that we have been doing. So this is one of the use cases that we're doing together with Rolls-Royce. And these aren't the nice cars. These are the airplane engines. And what they are doing is they're really calculating heavily the airflow within those engines. And an airflow calculation can be extremely computationally intensive. What we are doing is actually looking at, can a part of that calculation be done on a quantum computer? And actually the answer is yes. So we can map a part of the CFD equation to a linear set of equations. And the nice thing about a linear set of equations is that there's a quantum algorithm named HHL, which is able to solve that exponentially faster than a classical computer. So a perfect use case to use a quantum computer. So what is the outcome? So together with NVIDIA, we created this circuit. It had 39 qubits, and only the QPE part, I think, was already over 1 million gates. And so the entire circuit was 10 million gates or more, had 39 qubits, and we simulated that on a cluster of NVIDIA. And we believe that this is the largest quantum simulation that there has ever been done on a classical device. And the entire circuit has been created using the Classiq platform in the way that I've just proposed. So the end user just created a state preparation, QPE, amplitude loading, QPE dagger, and then a readout, and they got the entire circuit. So that's a really powerful thing. The end user doesn't need to know anything about the gates. Imagine having to program 10 million gates manually. That is simply an impossible task. Research. So our platform has been freely available to any researcher and student since the beginning of this year. So if you're in that group, always feel free to use it. What we have actually been doing with quite a lot of universities, also here in Germany, in Munich, for example, is using this tool to teach students about quantum computers. We think that the next generation of quantum programmers do not need to know and do not need to work at the lowest level of a quantum computer, just like computer scientists are not working on the lowest level of computers today either. And that is how we're trying to help universities get more people into quantum computing and enable more students to program quantum computers. And that's what we do with various universities all over the world. So with that, thank you so much, and I hope there are some questions.
Yeah, thanks for the talk. I understood that the simulation with Rolls-Royce was performed on a simulated quantum computer. Can you give us an indication of what the performance difference was of this quantum computer simulation compared to simulation performed on classical computers? Was it faster or slower or more accurate or less accurate?
I think the accuracy was the same. I think a traditional machine would still be able to do it quicker. It has been optimized for years and years. I think this was really a proof of concept that it works, that this algorithm works, so you can use it in this specific context. And of course, the idea would be that if we would have a quantum computer, then it would actually be quicker than a classical computer. But as far as I know, we don't have one which can do this.
Okay, thanks.
Are there any more questions? Yes.
So thank you for the very nice talk. Two quick questions. First, the optimization of the circuit design and layout. Is it also happening based on other attributes of the hardware, for example, some sort of noise model? And the second question is with respect to the integration of the hardware. So how would that look like from an end user perspective in terms of, I don't know, say I have some AWS credentials for Bracket, right? And I want to run it on their backends. Would Classiq basically handle all that, authorization, authentication type of the game as well?
Yeah, so to go to your first question about errors and noise, the answer is no. We will generate the optimal logical circuit. And there are transpilers, for example, with IBM, which take the latest gate data, gate fidelity data, and those type of things. That is something we don't do. So our idea is really create the best logical circuit. And what we see with that is actually we reduce the depth of logical circuits immensely. And that already really helps. I mean, translation optimization is really nice, but what if you have circuits which are like half the depth already in the beginning? Then that's what we're trying to target. And regarding the execution, yes, that's exactly what we do. So if you have IBM credentials, Azure, AWS, the moment you press execute, you can select on which devices. There can also be multiple. You can say execute, and it will prompt you for your credentials. And if you put them in, we'll do the rest. And you just wait until the results are there. And unfortunately, the wait can be a while, but we'll do the rest for you. Okay.
Okay.
Thank you so much.